Hey everybody, welcome back to Young Engineers of Today, the Mechatronics, Amazing Mechatronics edition. So on Tuesday we went over, well, working with multiple LEDs. And if you remember, the circuit itself was pretty similar to the stuff that you guys did with the single circuit. And the big deal was the fact that it was, come on, load. The difference on the programming side was really what we were concerned with. So this was the circuit we ended up building. As you can see, it looks very similar to our single LED, except we just have 8 LEDs and 8 resistors plugged into 8 separate pins on the Arduino. And then we had the programming side of things. Let me go ahead and bring that back up as well. Also, I will sing while I do it, apparently, because I can't control my own mouth. Let's open up our previous sketch, January 10th. Here we go, bam. So we got started on arrays and for loops. And by started on for loops, I mean I typed that out and went, I'll explain it to you on Thursday. But we did get started on working with arrays. I did explain arrays to you, which are essentially just collections of variables all in one spot so you can keep track of them more easily and manipulate them one at a time. However, there is an additional sort of ability with arrays, and that is you can basically access individual entries into an array by asking for their index number. So let's see here. How many of you have used a physical dictionary or a physical encyclopedia or a physical phone book? A couple people. But you guys are probably all pretty familiar with the concept. You flip it to the page that has the entry you want on it, and you look up the entry. But how do you know which page has the entry you want on it? Well, a lot of times they're listed alphabetically. In fact, they're pretty much always going to be listed alphabetically. And then you look for the particular letter you're interested in and look for your entry in that. Well, you can kind of think of the index number for an array like that alphabetization system. We want the ninth entry in an array, so we're going to ask for the ninth entry. That kind of thing. We want the fourth entry in an array, so we're going to ask for the fourth entry. Then the computer will dutifully provide us with the fourth entry, and then we can use it however we need to. Either we can change the value in it, or we can pull it out and use it in an equation, or we can, use it for some results or something like that. Who knows? We can print them all out in a line, whatever. There's only one caveat to that. You see, back in the day, when computers had, don't mind my wonderful explanation from earlier, back in the day when computers had a whole, 3 bytes of memory, every single bit of space on that memory mattered. Every single bit of space on that memory mattered. You had to make sure you were using all of it. In addition, when you're using binary in order to count something, you want to make sure that you're utilizing all of the numbers. So for that reason, so let's see here. We've got 1, 2, 3, 4. Let's put it this way. So learning how to count in binary, right? It's just sequences of zeros and ones. Using let's say using 2 zeros, we can count all the way up to 3. So 0, 1 is equivalent to 1, 1, 0 is equivalent to 2, and 1, 1 is equivalent to 3. So we can count all the way up to 3 using two digits. How many numbers can we count, though? How many different numbers do we have when we have 2 digits? Well, I'll tell you. We have 4, because we're forgetting one very important one here, and that is 0. So counting 0 in all of this, we have 4 numbers with which we can use for anything. We have 4 numbers we can use for whatever we need to use them for. And a lot of times, when you were dealing with, early computers and stuff like that, you were in situations in which, you maybe had the ability to count up to 15, as is the case here. You can really only, no, you can count up to, 32 here, 31 here. You can count up to 31. You might have 31, you can count to 31, but you do have 32 numbers because you have 0. So hey, if you're a computer scientist back in the day, or a software engineer or a computer engineer, if you only have the ability to count up to 31, if you only have 32 slots with which to keep track of either space in memory or, number of lines in a program or something like that, you might want to make use of all of those. So it's become convention at this point that pretty much anything computer related, counting starts at 0. And arrays are no exception. If you want to reference the first slot in an array, so like if we have an array of, I don't know, let's see here, 1, 2, 3, 4, 5, 6 values, that first slot in the array is going to be 0. And this one is going to be 1, and this one is going to be 2, this one is going to be 3, and 4, and 5. Why not 1, 2, 3, 4, 5, 6? Because that also goes up to 6. Well, again, consider the situation with 4 slots. We use binary to keep track of which slot we want. So if we have 4 slots, and we go 1, 2, 3, 4, well, we can count up from 1 to 3 using 2 digits, right? But with this third digit, with this 4th slot, we suddenly need 3 digits in order to be able to count all of the spaces in it. So it kind of screws everything up. We can no longer neatly and cleanly keep track of all of the spaces in the array with just 2 digits. And then on top of that, we're going to have a whole bunch of unused numbers when we go to 3 digits, because we're not using 5 or 6 or 7 or 8 or 9 or 10 or 11 or 12 or 13 or 14 or 15. We're not using any of those. Oh, no, that goes up to 8. Dorp. 5, 6, 7, or 8. So we're missing a whole bunch of values that they're just going to waste and not going up to, 8 spaces or 7 spaces. So for that reason, we start counting at 0. If we knock all this over one slot, so it becomes 0, 1, 2, 3, suddenly we can count all of the slots on this array with 2 digits. This is probably way more than you wanted to know about why this sort of thing happens, but I always kind of think it's sort of interesting to think about where this all used to come from. Nowadays, we have so much memory and so much space that it's kind of a moot point. However, these holdovers still exist because C still exists, C++ still exists. You know, it's the same way in Java because Java works on very, very small machines as well as, like, modern day computers. JavaScript, so it can take up less memory because JavaScript itself can be kind of uh, a memory hog, sort of. So on top of that, you work with what you know. So if you're used to counting from zero in computers, when you write your own language, you tend to start counting from zero. Now, this happens in an Arduino generally because the Arduino has a limited amount of space, and so we want to utilize it as much as we can. So we also start from zero here. So in that sense, this is slot 0, 1, 2, 3, 4, 5, 6, and 7. This is referred to as being zero indexed because the index numbers start, or the numbers for the index start at 0. So now if we want to access the first space in an array, we call for space 0. It's weird, but I wouldn't have it any other way at this point. It just feels very computery and efficient to do it this way. Anyway, so that's arrays. Let's talk about loops. So I'll spend, in which he spends another 15 minutes talking about some computer science concept. Let's talk about loops. So what I said on Tuesday was loops are good in case you want to have a thing that repeats a bit of code a certain number of times. And some of you, oh, here, let me pull up the YouTube channel for it. Oh, for sure. Yeah, the one that I recorded for Tuesday is actually a makeup because for some reason the recording that I had just decided to not work. So wonderful. Anyway, there you go. It's also got actually all of the other classes that we do, which looks like it's just me. Oh, in a few days? Oh, good luck with that. Yeah, I don't miss that. Okay, so sometimes you want to iterate a certain bit of code a certain number of times. And, we've got the thing here where it's just like all of this stuff and I just copy pasted it. That's totally doable. However, it's not ideal. Sometimes you want to run it 1,000 times or 1,000,000 times. Sometimes you don't know how many times you want to run it because one time when you run the program, you only want it to run 5 times. One time when you run the program, you want it to run 8 times. One time when you run the program, you only want it to run 3 times. So sometimes you don't really know how many times you want a bit of code to loop either, or repeat. So for that reason, doing the copy-paste thing, hard-coding it into the code, or hard-coding that in, is not always the best idea. It's not always something that you want to do. In fact, more often than not, it's not something you want to do. I mean, you might as well loop it anyway because it takes less typing on your part. So enter loops. Specifically for today, for loops. And loops allow you to run a bit of code a certain number of times, an indeterminate number of times even, sometimes, if you write it as such. And they're structured like this. So for loops always start with the for keyword. This tells the computer that it's going to be a for loop. And then we got a bunch of stuff in parentheses, and then we got some curly brackets, and the stuff you want to loop goes inside of the curly brackets. So basically, anytime a for loop runs, it will run the stuff inside of the curly brackets, however many times you tell it to. But there are 3 parts to what goes inside the parentheses for a for loop. And it's important to understand what each of them is meant to do so that you can build your own for loops and understand, you can look at for loops and understand exactly how many times they're supposed to run, or at least get a vague idea of how many times they're supposed to run. And they're like this. Let me write one down here. The first one is the initialization. The second one is the conditions. And then the third one is the iterator. So we got initializations, conditions, and iterator. What do those mean? Well, the initialization basically sets up the initial conditions for the for loop. Basically, the way a for loop works is it will run, it has a variable that it uses to keep track of how many times it's run. And each time it runs, it will change the value of that variable. And once the value of that variable is above or below a certain value or equal to a certain value, then the for loop will stop running. So the initialization creates our variable, sets it to a value, and lets our for loop know that it's going to be its signal variable. So we're going to say int and then I equals 0 in this example, and then a semicolon. All of these are always going to be separated by a semicolon. So here what we've done is we've created an integer variable and we've called it I and we've set it equal to 0. It's important to note that this right here can be called whatever you want. It doesn't need to be called I. However, computer science tradition, standards, things like that, generally dictate that the variable that's used here is going to be some single letter name. Most often it's going to be I. Sometimes it can be J, sometimes it can be K, sometimes it can be Z, M, N, any of those, but it's going to be some single letter variable for reasons that you'll see, in a minute, perhaps. But a big part of that is just convention anyway. So integer I equals 0. We've set up a variable, we've given it a name, we've given it a value, in this case 0. Then we're going to say, then we need our conditions. So as long as whatever's in the conditions is true, this is an important part, whatever is in the conditions, as long as it's true, the loop continues to run. So in this case, in our conditions, let's say I is less than 10. We've set up our conditions. So as long as I, this variable that we established initially, is less than 10, the loop will run at least one more time. So far, so good, right? Now we've got our iterator. The iterator is where the magic happens. So the iterator is how we change the variable every time the loop runs. And that's important to note. Every time we reach this line right here, the iterator will work on the variable in some way or another. Let's just use a very basic example. I plus plus, which is simply shorthand for being I equals I plus 1. Simply add 1 to I. So now, every time the loop runs, we are adding 1 to I. So the first time this for loop runs, I is 0, it runs. It hits the top again, I becomes 1. Is it less than 10? Yes, run again. I becomes 2. Is it less than 10? Yes, run again. 3, less than 10? Yes, run again. 4, less than 10? Yes, run again. 5, 6, 7, 8, 9. Is it less than 10? Yes, run again. 10. Is it less than 10? No. As soon as this bit here is false, it's going to skip everything inside the curly brackets and move on to whatever is after it. So in this example, how many times is this loop going to run? Any ideas? All right, all right. We got to vote for 11 times. Okay. Including 0. Yeah, there you go. We got to vote for 10 times. And we got to vote for 9 times. We got 2 votes for 10 times, 1 vote for 11, and a vote for 9 times. All right. So I starts at 0. So you got that part right. 0 is going to be one of the numbers we use for counting. Excellent. I is less than 10. So if I is 10, will this loop run? I mean 10, lol. So if I is 10, will this loop run? No, exactly, it will not. So it's going to run from 0 to 9. But remember when I was talking about 0 indexing for arrays and stuff like that? So that means that, after all, this loop is going to run 10 times. Kind of weird, right? You get used to seeing it, though. And you get used to being able to read it. So in this case, we're going to start at 0, we're going to count to 9, and we're going to stop after we run it the 10th time, which is 9, because we started at 0. Whatever. So this allows us, this could be 100, and then it runs 100 times. It could be 1 billion, and it'll run 1 billion times. I don't recommend that, but it could. It could be, 2, and it'll run twice. Whatever. Point being, we can change our initialization and our conditions. In fact, we can make it so that I is equal to 10, and as long as I is greater than 0, and we could subtract 1 from I each time and then have a countdown. Why might you do that, you might ask? That seems kind of useless because it's just doing the same thing, but now you're making the math more complicated. Why you got to make life harder? Why you got to make life harder? Well, I'll tell you. Here's the thing. As long as this loop is running, I is a variable that exists, right? We've already established that I is used to keep track of how many times that loop runs. Nothing groundbreaking there. However, since I exists within the context of this loop, it is a variable that we can mess with, just like LED pin. So inside this loop, we can say, let's print I. And just like that, every time this loop runs, it's going to print whatever is stored inside of I. So the first time it's going to run, it's going to print 0. Second time it runs, it's going to print 1, and then 2, and then 3, and then 4, and then 5, and then 6, and 7, and 8, and 9. And it'll print these out to the screen each in succession. And we've done that with 3 lines of code. Because we can leverage that variable. We can do stuff with it. I mean, we can modify it inside of this loop too if we wanted to, but I don't generally recommend that because things start really getting complicated if you start doing like, I plus 2 minus 9. And then it's like, okay, now where are we? Are we actually gaining any progress? Is the loop ever going to end? Answer is no. But is the loop ever going to end? Are we going to, I mean, it will eventually because of overflow. But anyway, are we really making progress towards ending the loop? When will it end? How many times will it run? Is the computer going to freeze up? Stuff like that. So it's generally not recommended to actually mess around with the variable inside of the loop. But, sometimes you need to do it. And sometimes Most of the time, in fact, when you're using a loop, you leverage the fact that you do have that ability to use the variable in something. So with all that in mind, what do you think is going on here in these 3 lines of code? This might look like, oh, I don't know, this variable up here. Maybe we're referencing the index value, the index number of a value in an array. Maybe, potentially, could be. So if we take this apart, it's a for loop. Duh. Integer I equals 0. We've got our I, it starts at 0. I is less than 8. So it's going to run 8 times, right? Because it's less than 8, but we start at 0. I plus plus. Add 1 to I each time. 0, 1, 2, 3, 4, 5, 6, 7. Pin mode, LED pins, the ith, and I had Mike Tyson talking about ice in his drink, the ith position of LED pins. So the first time this loop runs, it's going to be the 0th position. The second time, it's going to be the 1th position. The third time, it's going to be the 2th position. You can't really, I guess you can't really say first and second because it doesn't really make any sense. But whatever. Anyway, then there's going to be the 3rd, and the 4th, and the 5th, and the 6th, and the 7th. Coincidentally, the 0th, and the 1st, and the 2th, and the 3rd, and the 4th, and the 5th, and the 6th, and the 7th. The 6th, by the way, is the 8th, not the comma. And so it's going to replace this with whatever value is at that position. So when I equals 0, we access LED pin 0, so that this gets replaced with 2. So we're saying pin mode 2 output. Pin 2 is now set to output, then 3, then 4, then 5, then 6, then 7, and 8, and 9. You get the idea. So now we can actually apply this to this down here. Now we're at 45 lines of code, including the loop and the array that we've already created. Whoops, I didn't even follow my own advice. Bam! There we go. And let's see here. Digital write, LED pins, I, high, delay 1000, because remember we got to do our wait a second, digital write, LED pins, I, low, I said that part higher, delay 1000, and bam, 20 lines of code, including all of this white space in order to make everything easier to read. Whew. Whereas we had like 55 lines of code before I even did the compression up here. So look at that. We have cut our code by more than 50%. And we are accomplishing the same thing. And it is easier for us to understand what is going on here. It is easier for us to keep track and correct issues that might be in the code. We've basically just made our lives so much better. So let me go ahead and copy this stuff. And I'm going to paste it into here. And I'll bring the code window back up again if you need it. I just want to show off what exactly is going on here because oh my god. So upload and run. And just like that, each of these LEDs lights up in succession. One right after the other, and then it just restarts. You can actually, by looking at this and watching the LEDs light up, you can actually see the loop in action. You know exactly where you are in the code and exactly what loop number you're on. This is well, a digital representation of a physical representation of a loop, which I got unreasonably excited about. Man, I'm I'm easy to amuse. But hey, makes life a lot more fun that way. So there you go. As you can see here, loops make your life better. Um, Show of hands, does anybody else still need to look at this code? Okay, we got a few hands up, so I'll just go ahead. I'm going to keep it on this for about 2-3 minutes, just so you guys can compare it to your own code, make sure that everything's the same. And if you haven't typed everything out yet, then go ahead and do that as well. Let me extend this down a little bit more so you guys can see all of the code window in one go, even though they're just brackets down there. Come on, come on. Oh, it only goes up. Blah, blah. I'm going to shrink it just a wee bit. $26. Okay. There we go. Now it's all on there. So yeah, until about 8:35, and then we will get started on Hey, that was an excellent question. I have a question about the declaration of variables. Do global variables have to be declared outside void setup? Yes. And that gets into something called variable scope. Oh, there you go. So yeah, you already did this part then, James. We're going to get started on a new circuit here in probably about 5 to 10 minutes. Yeah, okay. So it's not so much that LED pins is our global variable because it's outside of setup. It's LED pins is our global variable because it's outside of either of these functions. It's outside of any of these functions. So in essence, the only thing that it's inside of is the program. So its scope is the program. So variable scope is basically a concept that allows computers to use their memory more efficiently. And memory and variable scope, memory, variable scope. I keep wanting to say memory. Variable scope dictates that a program, once it has declared a variable inside of a function, that variable, or in this case here with I, a loop, as you can see we used I twice here. Normally that's not kosher. However, since these are self-contained, they're contained within a loop. What? They're contained within a loop, which is contained within a function. As soon as this, let's start over again. When a variable is created inside of a function, it is considered to be property of that function, like a subvariable of that function, that sort of thing. As soon as that function ends, that variable is unceremoniously destroyed. It is promptly forgotten about by the computer and just sort of nuked. That memory slot becomes free again, and the computer moves on its merry way. It's very, very ungrateful, because the variable did all this work, and it was holding all this stuff, and the computer was like, hey, do some math, and the variable was like, no problem, computer, just let me know so I can hold on to it. Would you consider the void setup to be a misnomer? No, not necessarily, because void setup does stuff that's not necessarily related to variables. We created this, don't get me wrong, we created this so that we can more easily keep track and access the pins that affect our LEDs. However, we could have just as easily done what we're doing here without the use of variables. So instead of doing LED pins I, we could have changed the parameters of this so it runs from 2 to what? Less than 10. And whoa, what happened here? Whoa. I got all kinds of wiggly, confused. What is going on? Okay, so the cursor is not pointing towards where it's actually typing out, which is weird. I need an adult. There we go. Now it fixed itself. So we could do this. By changing the parameters of our loop, we can skip using this LED pins array entirely. The code in my void loop is displaying the error, I was not declared in the scope. Okay. Did you do integer I equals 0 in this for loop? Because it sounds like that could be what it is. Another thing you can do is, in case you run into an error, like a code error, like let's say we did boop, 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 boop. Hello, oh, right. Boop, 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 boop. Come on. Ah, this is in the way. There we go. Boop, 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 boop. Okay, so if we do that, as you can see, it says 12:7: error, I was not declared in the scope. That 12 colon refers to the line that it's on. That first number always refers to the line that it's on. The second number refers to, let's see here, 1, 2, 3, 4, 5, 6, 7, the character that it is on that line. So you can always just copy, and it also highlights the line usefully. If you could just copy paste the line that's highlighted and put it into the question box, you might be able to take a look and see exactly what's going on. But yes, so setup is set up for the Arduino proper. It actually has nothing to do with any of the variables that we have or anything like that. So it isn't necessarily a misnomer in that sense. It's just maybe referencing something that you weren't expecting it to reference. But yes, so anyway, as soon as a function that contains a variable, that a variable was created and ends, that variable is destroyed. So what we do is we keep it up here, so it's not inside of any particular function. No, it could not. That's another excellent question. Could everything inside void setup be outside void setup? And no, it could not. Because for this is an actual command here. And commands always need to be inside of, like, inside of a function. Yeah, exactly, since it's actually run. This is up here, so we have global scope, so its scope is the entire program. It's not forgotten until the program is finished. Generally, it's actually poor form to have a lot of global variables because you start running out of names really fast. You could accidentally manipulate the value for a variable in another part of your program without realizing it. You know, you're just typing and you're tired one night and you do something, you're like, oh, like I'll just add 3 to LED pins or whatever, and you promptly forget about it and you come back 4 days later and suddenly you're just getting weirdo garbage values everywhere. And it's because you forgot that you accidentally added that and it's on another separate page of code, that kind of thing, you know? So generally it's not the best idea. It's also not great from a safety standpoint because global scope variables can be changed from anywhere, including somebody else who has access to, like, to be able to poke around in your program while it's running. Don't recommend that. But regardless, the fact that we have it here, that's okay. This program is simple enough, and we do need to use it throughout the entire program. There are global variables aren't the devil. It's just they need to be used wisely. It's like salt. Some global variables will really enhance the flavor of your program, but too much and it becomes a mess. On top of that, there are other programming languages which have means to get around needing a global variable and stuff like that, with ways to pass that value to other parts of the program as necessary. Those also do tend to be much better ideas, but, whatever. For sure. I'm glad that helps. Um, any luck with copy pasting that, Melina? Oh, okay. Well, but your LEDs don't work now. Oh, that's no good. Um, they might be plugged in incorrectly. Because if you're not getting a code error, so okay, if you're not getting a code error, that rules out a syntax error. So it could be a logic error at this point, or it could be an error with the circuit, and that's always the tricky thing about this is when you're working with physical computing, you're never really sure whether it's a code error or if it's a circuitry error. So hmm, we can take a look at it at the end of class, um, and figure that out. For now, though, let's go ahead and we'll shelf this one. Um, and let's take a look at what we're going to be working on next, because it's already 8:45. My phone is going insane, and I don't know why. uh, okay, so arrays, pulse width modulation. What? Well, that's kind of neato. Make them breathe. Let's not worry about that for now. Let's do the next thing we've got, because I want to make sure I cover as many sort of concepts as I can with you guys, in order to expose you guys to as many, well, concepts as possible. Aha! Plus, lesson 4 is input. So now we get to mess with buttons and stuff. So, I guess I'll spend the next 10 minutes talking about analog versus digital and this kind of stuff, and then we can maybe get started on the circuit, um, and then we can break for the weekend, and I can help you out with your circuit, Melina. Um, okay, so inputs, because stuff just isn't as exciting unless you can interact with your Arduino while it's running. I mean, so far what we've done is we've made LEDs blink, which is pretty cool. It's pretty neato. But the LEDs haven't like blinked faster or slower because, the temperature has changed, or, you haven't been able to like, turn on a light and have the thing freak out and start blinking super fast or something. Like that's not a thing that we've there's only one half of the equation here. It's been all output. Let's spend some time learning how to mess around with the inputs, because the Arduino is all about the intelligent management of inputs and outputs. It's about taking inputs, figuring out what to do with them, and turning them into outputs that make sense to us. I mean, among other things, obviously we can do some nice structured outputs as well, just with some code and some LEDs, but Um, Introducing inputs into the equation makes a whole lot of things more possible now. So, this inputs lesson goes over analog read, digital read, and actually we do a diversion into serial print, which is a very useful thing. So I will be absolutely certain not to skip that because that's incredibly important when you're working with an Arduino. Having the serial print allows you to see into the brain of the Arduino and what it's actually doing, which is just absolutely invaluable for debugging purposes, figuring out what's going wrong and where. So analog read. I explained to you guys the difference between analog and digital, right? I spent a little bit of time explaining it. Did it really make sense at the time? Or does it bear repetition? Okay, we got one vote for makes sense and one vote for could you give a refresher? Certainly. Um, all right, so digital, ones and zeros, right? Like computers are all ones and zeros. So it's a binary or dual value. Binary having to do with two numbers or two values rather. Oh, look at that wonderful for loop bean. Um, I don't know, it's shaped like a bean. I don't know why I said that. So 0 and 1, right? So we only have two values, either full off or full on. If we were to look at maybe a graph of the electrical current output by a digital circuit, it might look something like this, where we've got full off and full on. It's one or the other. There's no in between, and that's why you have these vertical lines here, because they represent basically an instantaneous change from full off to full on. Pardon me for a moment. So yes, full on or full off, because there's an instantaneous change. You don't have any values in between, so it could be said that digital has only two values available to it, either off or on. So imagine it like the light switch in your room or in your bathroom. It's just the lever and you flick it and either the light's off or the light's on. Analog, on the other hand, where digital is said to have two values, analog is said to have an infinite number of values, which is weird, but it'll make sense in a minute. So let's go back to our example. Let's assume that these are volts that you can send out either. So you can either send out 0 volts or send out 1 volt. With analog, you can also send out 0 volts. You can also send out 1 volt. However, analog can also send out any value in between. So a graph for the power output of an analog circuit over time might look something more like this. Something like that. I mean, it doesn't necessarily have to, but it could. So it could send out 0 volts, it could send out 0.1 volts, it could send out half a volt, it could send out 3/4 of a volt, it could send out 6/10 of a volt. So any value from 0 to 1, which is why it's said to have an infinite value, because you could send out 0.5. Yeah, you could dim an LED, exactly. So have you ever seen those light switches that are just the I don't know, the little wheels, and you could turn them and make the lights dimmer or brighter? That is an analog circuit versus the light switch digital circuit. So you got the light wheel analog and you got the light switch digital. So that is the difference between the two. Both are very important because having something like a threshold like digital has, where it's either off or it's on, works very well for stuff like computers, because then we can utilize the various combinations of on and off and all these intersecting and splitting circuits and everything like that, and we can create a whole language of logic around it like we have, which is why right now I'm yelling at my screen, and you guys are listening to me yell at you some number of miles away. On the other hand, having an analog set of analog values can be very useful too, because then you can read all of the shades of gray in between. For instance, a photocell is a very useful analog component. It's also known as a light-dependent resistor, but what it does is its resistance actually changes based on the amount of ambient light it's picking up. So the brighter its surroundings, the less it's able to resist in a circuit. The darker it becomes, the greater its resistance becomes. And it does it in a gradient. It's not just full resistance, no resistance, full resistance, no resistance. It can resist half power or a third power or two-thirds power or whatever. You get the idea. I'm repeating myself now. But you remember how I said the Arduino can read this kind of stuff? So just spitballing ideas here, you can have a LDR hooked up to a set of lights, and the lights, the LEDs could be RGB LEDs, and the LEDs could turn gradually from blue to red based on the amount of ambient light. As it gets darker, the lights will gradually change color towards red. You could have I don't know. You could have a screen dimmer. As it gets darker, the screen on your computer gets dimmer. I wouldn't recommend putting aftermarket mods on your monitor like that, but you could totally do it. Versus analog. You have a button, you press a button, light goes on, don't get me wrong, digital is pretty amazing, but there's having both of these options expands the possibilities for circuits and ideas and things like that. Well, now that I talked about that, that actually took up the last 10 minutes. So let me go ahead and do the poll questions, and then I can leave it open for question and answer time. And again, I haven't forgotten about your circuit, Melina, so I'll help you out with that after we are after we're finished with after we're finished with the poll questions, and we'll try and figure out why exactly it's not working. So let me go ahead and do that. If you have any questions about anything, feel free to ask them after we've done the poll questions. Otherwise, you're more than welcome to head out. Have a great weekend, and I'll see you on Tuesday.